Today we're going to talk about, we're actually going to review for exam 4 on chapter 6 and 7. And I've got some, this is the review document that was distributed through Brightspace. And I picked out some of these problems, some of these questions as representative of the questions that might be on the exam. So I've highlighted them just to keep me on track. It's awful dark. That's a little better. Okay. So let's take these one at a time. And we've got, how long do we have? Little under 2 hours. Should be able to complete this review. Number 1. Which of the following statements is not true of balancing in a chemical equation? Which is not true. So since every potential answer is unique, then all we have to do is work down until we find the one that's not true. How about the first one? Subscripts in the reactants must be conserved in the products. Is that true? Subscripts conserved? Before you even try to balance an equation, the reactants and products must be written correctly. And the subscripts are the vehicle to writing a correct formula. So the reactants and products are independent from one another. The subscripts are not conserved necessarily. In fact, they are not conserved. If they happen to be the same for any of the elements in the reactants versus products, it's purely coincidental. So A is false. Your objective is not to conserve subscripts. Your objective is to be sure that you have the same number of atoms of each of the elements on both sides of the equation. So coefficients are used to balance the atoms on both sides. That's true. So B is true. Phases are often shown for each compound, but are not critical to balancing an equation. That's true. The law of conservation of mass must be followed. The conservation of mass is an outcome of the balancing process. When you have the same number of atoms on the reactant side and the product side for each of the elements, you will automatically have the same mass, total mass of reactants and products. Atoms are neither created nor destroyed during any chemical reaction. That's true. So B through E is true, A is false. All right. So let's see who's next. Let's turn this thing on first. 3. I don't know if I can. No. I have to do this manually. Let's see. We can get 2 on there at once. Number 3. When the following equation is balanced using the smallest possible integers, what is the number in front of the substance in bold? Okay. So we have to start with an equation that's not balanced.
H3PO4 plus HCl.
Okay. All right. So the first question that comes to my mind is, are these written correctly? We assume they are. Phosphorus pentachloride, right? It could be any combination of phosphorus and chlorine because they're both nonmetals. So we can't balance charges here, so we have to accept that as is. Water is given. H3PO4, PO4 is a polyatomic ion with 3- charge. Hydrogens, when they're in this position, are always +1, so 3+ is balance of 3-, that's true. And HCl, that's true. Okay, so these are written correctly. Now we need to balance it. So let's use our budget method. So we have a phosphorus here, we have a chlorine, we have hydrogen, and we have oxygen. So count them up. There's 1 phosphorus, 5 chlorines, 2 hydrogens, and 1 oxygen. Let me see if I counted those right. 1 + 5 is 6, 7, 8, 9. 6, 7, 8, 9. That's correct. Okay, phosphorus on this side, we have 1. Chlorine, we have 1. Hydrogens, we have 4. And oxygens, we have 4. Okay? So, where do we start? Well, there are no single elements on either side of the arrow. So we can't hold that in reserve. So we just start where we want to. Let's say we want to balance the chlorines first. That means we need a 5 here. That'll give you 5 chlorines, but it'll also change the number of hydrogens. 5 + 3 is 8. Okay. If we balance the hydrogens, we need hydrogens occur in one place here. So if we put a 4 in front of that one, that'll make 8 hydrogens. It'll also make 8 oxygens. No, 4 oxygens, excuse me. 4 oxygens. And we're balanced. So the number in front of the bold is 5, which is D right here. All right, let's do number 4. All of the following are clues that a chemical reaction has taken place, except. So we're looking for the one that's not a clue for a chemical reaction. A solid forms. Like when you put 2 solutions together, does a solid form? That would be evidence of a chemical reaction. So A is true. The reactant is smaller. What does that mean? The reactant is smaller. If you can measure the reactant, does some reactant disappear? That's not a clue. That's a quantitative, that's an analysis of the situation. And that's not considered a clue. That's what you do when you know a chemical reaction has occurred. Then you can measure the amount of reactant that you start with and the amount of reactant you have left over. That's not considered a clue. Bubbles form, yes. Color change occurs, very likely. A flame occurs, definitely, a chemical reaction. So the best answer, whenever you've got a choice to make and you think that they're not all acceptable answers, pick the best one. The best one for this one, the one that is most likely to not be a clue, is the reactant is smaller. In fact, that's one that we did not discuss. So B should be your answer for that one. All right. How about number 5? We can just barely see number 5 there. Let me scroll it a little bit. Yeah, number 6 is available too. So we'll get 5 and 6 at the same time. Number 5, When the following equation is balanced using the smallest possible integers, what's the number in front of the substance in bold? And the one in bold is Fe, which is iron. So let's do this. Aluminum plus Fe3O4 yields Al2O3 Fe. Okay. Let's see, I didn't leave enough room here. There we go. Okay. Aluminum's +3, oxygen's a -2. That's right. That's right. That's right. This one is the squirrely one. Fe3O4 is you can't balance the charges for that one. You have to accept that one. And I'll prove it to you. Oxygen is usually a -2, so that's a -8. So how do you get a -8 from 3 irons? Right? The charge would have to be 8/3. Right? So the answer to this one is that you just accept it the way it is, as given. Actually, Fe3O4 is believed to be a combination of 2 oxidation states for iron. And we just combine it in this form because it's more convenient. So don't worry your heads about that one. In this case, just accept it as is. And then how do we balance this then? Well, we've got aluminum over here, and we've got an iron separate over here, so we can hold those to the last. Well, notice we've got 4 oxygens here and 3 there. One of those hints, those tricks that I showed you in one of the slides and in the document on balancing equations is, if you have a situation like this, where this element is in one place here and one place here, but there's no way that a coefficient will give you the correct number from the other side, then try cross multiplication. So we put the 3 over here and the 4 over here. Now we have 12 oxygens and 12 oxygens, but we also have 9 irons. So we need 9 irons, and we have 8 aluminums, 8 aluminums. Right? Notice I didn't use the budget for this one. You can use the budget, that's fine. But all we have to do now is count them up and be sure. So 8 aluminums, 8 aluminum, 9 irons, 9 irons, 12 oxygens. Is that right? 12 oxygens? Yes. And 4 times 3 is 12 oxygens. So the equation is balanced. And the coefficient in front of the iron is A, 9. I picked that one out because of that cross multiplication trick to show you that it does work. Number 6, which of the following statements about chemical reactions is false? Here's another one where we're looking for the wrong one. So the rest of them should be true. In balancing the chemical equation, A, all subscripts must be conserved. We did this one before. I think this is repetition. It's a different version. It's the same answer, but a different version. This one is definitely false, right? We've discussed that one before. The subscripts in a balanced equation tell us the number of atoms in a molecule. That's true. Yeah. When one coefficient is doubled, the rest of the coefficients in the balanced equation must also be doubled. The key here is that the equation is already balanced. Notice that statement here, in the balanced equation. Once the equation is balanced, if you can multiply the entire equation through by some constant, some value, and it's still balanced. So C is also true. An individual coefficient in a balanced equation is meaningless. Well, yeah. The individual coefficient only has value insofar as it gives you the same number of atoms in the compound as for reactants and product side. Right? So an individual coefficient doesn't mean anything until it's taken in context. The phases in a chemical reaction tell us the nature of the reactants and products. That's true. Solid, liquid, gas, or aqueous solution. Those are the only ones that we've discussed so far. So A is the bad one, the wrong one for 6. Number 7. When the following equation is balanced using the smallest possible integers, what's the number in front of the underlying substance? So what's the coefficient in front of oxygen? All right, so here we better use the budget method on this one. There's, let's see, let me put it over here. C2H6, which is a hydrocarbon, oxygen. And to balance this, we don't need the phases. So I'm going to leave the gas phase out. They're all gases. And this produces carbon dioxide and water. Okay, now let's add them up. There's carbon, hydrogen, oxygen. So we have 2 carbons here, we have 6 hydrogens and 2 oxygens. On this side, we have 1 carbon, we have 2 hydrogens, and we have 3 oxygens. Okay. Now you may be tempted to try cross multiplication here because you've got an odd here and an even there, but we can't do it because oxygen occurs in 2 different places here. It won't work. So where do we start? Well, we don't start with the oxygens because that's a single element. We'll hold that one till last. So let's start with carbon. We need 2 carbons here. Okay. That makes 2. Now that changes the oxygens to 4 plus 1 is 5. Okay. How about hydrogens? Well, we need 6 hydrogens. So if we put a 3 here, that gives us 6 hydrogens. It also changes the oxygens. 3 plus 4 is 7. Okay. Now we need to balance the oxygens. We need 7 oxygens on this side. So I'm going to use the fraction trick. If we take 7 halves, then we get 7 oxygens. Okay? Technically the equation is balanced now, but we want the simplest whole number ratio. So we got to get rid of that fraction. How do we do that? We multiply the entire equation through by a number 2. Okay, so that puts a 2 in front of this one. That cancels the 2 here, right? Denominator, numerator cancels. So we have 7 there, we have a 4 here, and we have 6 there. And we've used up that 2. So our coefficients are 2, 7, 4, and 6. Which one are we interested in? The one in front of oxygen, which is 7. So that's why the answer is E. Okay. All right. Number 7, moving on. Let's see here. 10, I'm going to have to work on that one. Yeah, we get 10 and 11. Number 10, when the following equation is balanced using the smallest possible integers, what's the number in front of the underlying substance? So we want the coefficient for water. All right. Let's use the budget. So I need to leave myself a little space here. Al2O3. Al2O3 plus H2SO4. Remember your nomenclature? This is an aqueous solution of H2SO4, which means it's an acid. Right? It's got those hydrogens. So how do we name an acid? This is the sulfate polyatomic ion. And with oxygen in here, we don't use hydro to begin with. We just take this polyatomic, it's sulfate, 8's become X. So it's sulfuric acid. And then we have this compound, and I'm checking as I go in my head, are these balanced? And so far, so good. They are balanced. The compounds are written correctly. The equation's not balanced yet. We haven't done that. So we have 2 aluminums here. We have, okay, we're going to use another trick. Notice that we've got oxygen in 2 places. But this sulfate stays intact on both sides. So we're going to use an oxygen separate here, just those 3. And then we're going to use, got to do hydrogens and sulfates. The sulfate group is only 1. On this side, we have 2 aluminums, 3 sulfates, and 2 hydrogens, and 1 oxygen. Okay. Now, we don't have any elements that we can hold out, so we just pick a starting point. How about oxygens? So we have 3 oxygens this side, we want 3 oxygens on this side. That's 3. That changes the hydrogens to 6. Okay. So now if we do the hydrogens on this side, we need 6 hydrogens. That means 3 here. So that's 6 hydrogens. That changes the sulfates to 3. So we have 2, 3, 6, and 3. That equation is now balanced. And we use the trick where polyatomic ions that occur on both sides can be used as balancing groups. So water, coefficient of water is 3. There it is right there. All right. It looks like we got another balancing coming up. So let's put the unbalanced equation up here along with its question number. And what's the number in front of the hydrogen? So we're starting off with 10, reacting with sodium hydroxide, yields this compound. That would be sodium stannate. This is a polyatomic ion here. Okay, plus hydrogen. Okay, all right. So we're going to hold the 10 out and the hydrogen out. And it looks like we probably ought to do the budget to keep things from getting messed up. So we got 10, sodium, oxygen, and hydrogen. Okay, got 110 here, 1 sodium, 1 oxygen, 1 hydrogen. On this side, we have 110. Sodium, we have 2. Oxygen, we have 2. And hydrogen, we have 2. Okay. All right. So let's see. The 10s are okay. The sodiums need adjustment. So we have, if we put a 2 there, that gives us 2 sodiums, 2 oxygens, and 2 hydrogens. And it's balanced. So what's the coefficient in front of hydrogen? There's no number there. If there's no number there, but you have the compound or the element, you know there's at least 1. So the coefficient is 1. Right here. By the way, if you balance an equation and the question asks you for the total of the coefficients, add up all the coefficients and what's the total value, don't forget there's a 1 here, there's a 1 here, and there's a 1 there. All right. Let's see, it's a lot of repetition, so we're skipping down. There we go, 24. That doesn't mean you shouldn't attempt those others. That just means there's a lot of repetition in here, and I do that for a reason. Remember at the very beginning of the semester, I told you your two best friends in this course are curiosity and boredom. You always want to know more. That's curiosity. Boredom is you're working these problems and you start to see a pattern. And you work the same type of problem over and over again, you get bored doing it. If you get bored working a problem, that means you know it pretty well. And it's time to move on. (24). We're going to balance this equation. What's the number in front of the underlying substance? Silver nitrate. So we're starting with lead. And we're reacting with silver nitrate, aqueous solution. And that produces lead 2 nitrate. How do I know that that's a lead with a Roman numeral 2? Because nitrate is a -1. And 2 of it means -2, so the lead has to be a +2. Same, and well, over here there's no charge because that's a pure element. And then the last one is silver. Okay, so let's balance this thing. I think we can do this one. Since we've got an element here and an element here, I think we can do this one without setting up the budget. We've got 2 nitrates on that side, so we need 2 nitrates on this side because they're balancing units. Right? So now we have 2 nitrates, and we need 2 sulfurs. And we've already got 1 lead, so that's balanced. So what's the coefficient in front of silver nitrate? Is 2. Right here. See, some of them are easy, really easy. And you can save time if you don't need to set up the budget. All right. Let's see. Yeah. Oh, there's one. Okay. Let me scroll it. In this case, now there's the answer, but I'm going to show you how we got there. 33. This type of problem gives you a reaction in prose. It just writes it out. It names the compounds. So that's why early on, I wanted you to learn how to write compounds from their names and write names from the compounds. Because when you're confronted with a problem like this, you're not given the formula. You're given the name, and you have to write the formula. So let's balance the equation. Iron 3 oxide. We know it's got iron in it, right? And we know it has oxygen. So how do we balance that? Well, what type of compound is it? Remember, type 1, type 2, or type 3? Well, there's a metal there, so it has to be 1 or 2. Then we say, okay, what type of metal is it? Does that metal have a fixed charge, or could it be variable? And in this case, iron has a variable charge. So that means, and we can also tell that from the name, iron 3 oxide. That tells us that iron is 3+ charge. What's oxygen? Well, oxygen is a chalcogen, which means it's a -2. Okay, so we bring the 3 over there and the 2 over here. There's our compound. That's iron 3 oxide. All right, now we're going to react it with carbon monoxide. Carbon and oxygen are both nonmetals. That means it's a type 3 compound. And we have to say exactly how many of each element is in the compound, which we do. Carbon means there's one. And then monoxide, mono means one. So there's carbon monoxide. And what does it produce? Well, iron metal. Right? So we can put the phases in here. That's a solid, that's a gas. This is a solid. And it produces carbon dioxide. Carbon dioxide. Now that we have the compounds and the elements, the reactants and products written correctly, we can go to balance it. If you don't write them correctly first, then you'll never balance the equation. All right. So let's do a budget. Iron, oxygen, carbon. So we have 2 irons, 3 plus 1 is 4 oxygens, and 1 carbon. And on this side, we have 1 iron, we have 2 oxygens, and we have 1 carbon. Okay. So we're not going to mess with iron yet because it's an element. We're going to save it. That's one of the tricks. So we're going to do oxygen. Okay. We need 4 oxygens on this side. Okay. So that gives us 4 oxygens, but it also gives us 2 carbons. Right. How are we going to balance the carbons on this side? Well, if we put a 2 here, that makes 2 carbons, but it also makes 2 plus 3 is 5 oxygens. Okay. All right. So we need 1 more oxygen on this side. I'm toying with the idea of using a fraction. What if, see, we've got oxygen in 2 different places here. What if we, need another oxygen here, if we make that a 3, that increases this one to 6. Let's try that. 6 oxygens. Now, how do you get 6 oxygens on this side? Well, you've already got 3 here, so you only need 3 there. So that should do it. Yeah. So we have 3 carbons. We got 3 carbons over here. We have 6 oxygens, 3 plus 3. And we need 2 irons. We haven't done that yet. 3, 6. We need 2 irons here. That balances the equation. Okay. This is one that might require a little trial and error. You may, if you don't do it that way, you may find yourself with very large coefficients here down the road. And if that's the case, just check to be sure that those are the smallest whole number coefficients. If you can divide them through by some number, then do it and reduce the size of the coefficients. And you should, once you get it balanced, you should come back to this level, 1, 3, 2, and 3. All right, that was 33. Let me see. Yeah, there's several in here. Ah, here we go. I highlighted this one. All right. So for this one, you're actually given the compounds and you just have to balance them. So let's see, we have silver nitrate. We have calcium chloride. We have silver chloride. And we have calcium nitrate. Okay. All right. So we've got a nitrate here and a nitrate here. We can use that as a balancing unit. We've got one silver, one silver. We need two nitrates. So let's do this. That gives us two nitrates. We need two silvers. That gives us two silvers and two chlorides. And we got two chlorides here and one calcium, one calcium. So that balances our equation. Notice that the driving force for this reaction is the formation of a solid. Right? This is an aqueous solution, that's an aqueous solution. And this solid forms from that reaction. That's the precipitate. And that drives the reaction because this solid, when it forms, drops out of the solution. It's no longer available for any other reaction. It couldn't even go backwards. At least not under these conditions. All right, let's look at some more. Oh, 40. Okay. This one looks like it might be challenging. So we're given the compounds. So let's say 40. And let's start about right here. What is this compound called? Magnesium has a fixed charge of 2+. When nitrogen is in the anion position, it's in the second position, it's always a 3-. So we would say, instead of nitrogen, we'd say nitride. Magnesium nitride is this compound. And of course, this is water, pure liquid. Then this one, I don't know if you recognize it, this is ammonia. And then the final one is magnesium hydroxide, solid. Okay. Notice this is a polyatomic, but it's not over here. So we have to balance these element by element. We don't have any special tricks that we can use here. And there are no elements on either side that we can hold out. So let's do our tally first. Magnesium, nitrogen, hydrogen, and oxygen. So you have 3 magnesium, 2 nitrogens, 2 hydrogens, and 1 oxygen. On this side, we have 1 magnesium, 1 nitrogen, 3, 4, 5 hydrogens, and 2 oxygens. Okay. Let's see, where do we start? Well, I don't have any special intuition here. Let's just start at the top. 3 magnesiums. Okay. But that changes the number of oxygens. So 3 times 2 is 6 oxygens. And 3 times 2 is also 6 hydrogens, plus 3 hydrogens is 9 hydrogens. Okay. It's our new position. Now, how about nitrogen? We need 2 nitrogens, correct? 2 nitrogens. That changes the hydrogens again. So we have 6 hydrogens here, and we have 6 hydrogens there, right? 12 hydrogens here. Let's see. We need 12 hydrogens over here. So if we put a 6, that'll give us 12 hydrogens. Yeah. And that'll also give us 6 oxygens. And look at there. We are balanced. And you can tell with this budgeting system, 3, 2, 12, 6, we know we're balanced. We just need to check it and be sure. Well, that's a 1, so we can't reduce that one any further. That's the balanced equation. All right, let's see what else we got. There's several in here. Let's try. Okay, we'll try this one. This one looks like it's not too difficult. So we have hydrochloric acid, HCl, and calcium hydroxide yields what? Calcium chloride plus water. Okay. So let's set up our budget. Hydrogen, chlorine, calcium, oxygen, and hydrogen. Oh, we already got hydrogen. Okay. So we have one hydrogen plus two hydrogens is 3 on this side. We have one chlorine, we have one calcium, and we have 2 oxygens. Let's see, that's 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. It's good. Hydrogens, we have 2 on this side, 2 chlorines, 1 calcium, and 1 oxygen. Okay, where do we start? Well, again, hydrogens are in 2 different places here, so we can't cross multiply with this 3 and a 2. So we could start with this one, chlorine. Right. Let's put a 2 here. Right. That gives us 2 chlorines, and it gives us 2 plus 2 is 4 hydrogens. Okay. Now we can do a 2 in front of this one. That gives us 4 hydrogens. And it also gives us 2 oxygens. 4, 2, 1, 2. We're balanced. Sometimes you get lucky like that. That was 51. Okay. How are we doing on time? Okay. Coming up on 1 hour. 53. Let's give this one a whirl. We've got sodium borohydride. Sodium borohydride. Okay. We've got boron trifluoride. We have sodium borofluoride. That's a 4, yep. And diborane. Now these, the only one in here that I would expect you to know how to name is this one, because that's a binary compound. These are not binaries. And this one is a special case. So if you can name that one, that's good. The rest of them, I just happen to know what they are, what they're called. Okay, so let's set up our budget. We have sodium, we have boron, we have hydrogen, boron again, and fluorine. So we have 1 sodium here, we have 2 borons, we have 4 hydrogens, and we have 3 fluorines. So let's see, that's 7, 8, 9, 10. 1, 2, 6, 7, 8, 9, 10. Okay, 1 sodium on this side, 3 borons in 2 different places. And 2 places here also. That could complicate things, but we'll cross that bridge when we come to it. 6 hydrogens and 4 fluorines. So this is 10, 14. 1, 2, 6, 7, 8, 14. Okay, so our initial tally is correct. Let's try to balance. I'm not going to tackle boron yet because it's in two different places on both sides. So let's move down to hydrogens. Hydrogen only occurs in one place on both sides. Right? We need 6 hydrogens on this side. Well, that's a problem. What if we try to find the least common denominator? What would be the least common denominator for these two? It would be 12, wouldn't it? Remember fractions? Right? 4 goes into 12 3 times, and 6 goes into 12 2 times. So if we put a 2 in front of this one, and a 3 in front of this one, okay? It's not exactly cross multiply, but it is a simultaneous coefficient insertion to give us 12 total. And so that would be 12 hydrogens here. And this would be 12 hydrogens. Now let's fix the rest of it. This is 3 sodiums here, right? This is 3 borons plus 1 is 4 borons. And hydrogens. We did hydrogens, 12 hydrogens, sodium, boron, chlorine. Okay, that's good. Now let's fix this one. We still got 1 sodium. We've got 4 plus 1 is 5 borons, right? And we've got 12 hydrogens and fluorines. We still got 4 fluorines. Okay. We need 3 sodiums right here. So if we do that, what does that do to our balance? 3 sodiums, 3 borons plus 4 borons is 7 borons, correct? Three plus 4 is 7, yeah. And we've got 3 times 4 is 12 fluorines. Okay, now look what we've got on this side. We've got 3 borons here, right? 3 borons out of 7 leaves you 4. Right, so we need 4 more borons. 4 borons plus 3 borons is 7 more. Okay, what does that do to the rest of it? Okay, we change this one. So that's 12 fluorines. And we're balanced. Okay, that one took a little bit of work. So, this type of reaction would not become easy unless you worked a lot of them. So that's why I give you all these to do, so you have experience. Okay. Where's my next one? There it is. 61. So we want to balance this equation. All right, C3H7OH. Let's see, need some space here. C3H7OH. You don't know the name for that one, but I do. That's called propanol. I'm not sure what kind of propanol because there are several kinds. But we are going to burn it. Right? This is a combustion reaction. We add oxygen and burn it, and we get carbon dioxide and water. Okay? So let's set up our budget. We got carbon, hydrogen, oxygen. That's it. Okay, 3 carbons here, 7, 8 hydrogens, and 2, 3 oxygens. Let's see if I did that right. That's 10, 11, 12, 13, 14. So this is 11 and 4 is 14. That's right. 1 carbon, and 2 hydrogens, and 1, 2, 3 oxygens. Okay. So we're not going to mess with oxygen. Well, first of all, oxygen's balanced right now. Plus, it's a single element. So we're not going to mess with oxygens. So we got a choice, either carbons or hydrogens. In this type of reaction, I usually start with the carbons. So we got carbon here, there's 3 of them. We need 3 carbons here. That takes care of the carbons. Now we have 6, 7 oxygens. Right? Okay. Now, how about oxygens over here? Well, we got hydrogens. We got 8 hydrogens. So let's do 8 hydrogens first. We need 4 here. That gives you 8 hydrogens. And now the oxygens change again. So that's 4 plus 6 is 10. Okay. Now, the problem on this side is that you've got oxygen in 2 different places. So if we excuse me. I'm going to do a recount just to be sure. 3 carbons, hydrogens, 8 hydrogens, 3 oxygens. Okay. 3 carbons, hydrogens, 8 hydrogens, and 6 plus 4 is 10 oxygens. Okay. So the count is correct up to this point. Now, how do we get 10 oxygens on this side? Well, we've already got 1. So 1 from 10 is 9. We need to have 9 oxygen. We need to have 9 oxygens here. Right? If we want to have 10, then we've got 1 here, and we can use this one to give us the other 9. Correct? So that would be 9 plus 1 is 10. That's balanced. But it's not the simplest whole number. So how do we get rid of that fraction? Same as always. Multiply by the denominator. So that'll give us a 2 here, a 9 there, a 6 here, and an 8 there. And we use this one up. So we have a 2, 9, 6, and 8. A 2, 9, 6, and 8. At 61. 62. I haven't checked my list to see how we're coming here. All right. I bet I'm going to run out of time. So let's do this one as quickly as we can. Fe2O3. Notice these are supposed to be subscripts. When I set this PDF file up, I didn't enable subscripts. So that's an error on my part. So this is Fe2O3. Now that one will balance. That one will balance charges. Plus carbon monoxide yields iron 2 oxide plus carbon dioxide. Okay. So we've got an iron, we got oxygen, and we got carbon. 2 irons, 3, 4 oxygens, 1 carbon. Oops. 1 iron, 3 oxygens, and 1 carbon. Okay. We don't have any elements to hold out. So we need 2 irons over here. I'm going to start with iron. That makes 2 plus 2 is 4 oxygens. Okay. And lo and behold, we're balanced with 1 coefficient. All right. So let's put on our running shoes. $68. All right. So we've got C8H18. That's octane. That's the stuff that you burn in your gas tank. Well, you draw it from your gas tank and burn it in your engine. That's the stuff. This is the primary ingredient of gasoline. And this is the reaction that occurs inside your engine, ideally. Okay. Now, we've got carbon, hydrogen, oxygen. We got 8 carbons, 18 hydrogens, and 2 oxygens. We got 1 carbon, 2 hydrogens, and 3 oxygens. Okay. We're going to hold that oxygen out till last. So let's just start with carbon. 8, 8. So that makes 16 plus 1 is 17 oxygens. Correct? And we've got 18 hydrogens. So we need, they only occur in one place. So 9 here would give us 18 hydrogens. That's good. But it also gives us 9 plus 16 is 25. It gives us 25 oxygens. Okay, how do we get 25? These are balanced. How do we get 25 here? The usual fraction. Okay. Now we want to balance that. So we multiply everything through by 2. That's a 2 here. That makes that 25, makes that 16, makes that 18. That's the balanced equation for the combustion of octane. All right. Looks to me. Okay. 73. Can we scroll out so we can get the whole thing? 73. An aqueous solution of ammonium carbonate is allowed to react with an aqueous solution of nickel 2 chloride. What's the solid in this balanced equation? Okay. So we have to write ammonium carbonate. Ammonium is that with a +1 charge, and carbonate is that with a 2- charge. So that means we need 2 of these. Go. And that's aqueous solution. And we're going to react that with nickel 2 chloride. So we have nickel with a 2+ charge and chlorine with a -1 charge. That means we need 2 of these. Okay. What does that give us? In this type of reaction, it's a double replacement. In other words, we swap partners. The ammonia goes over here, the nickel goes over here. Okay. So what do we get out of that? We get nickel 2 carbonate. Right? 2 minus, 2 plus, that's it. And then ammonium chloride, +1 -1. Now is the time for you to look in your solubility chart and find out if one of these is a solid. This one is in aqueous solution. It's soluble. This one is a solid. That's your precipitate right there. Okay. Incidentally, is this balanced? Well, we got one nickel, we got one carbonate. We need two ammonias and two chlorides. So that would be balanced. And 73. Okay, 75. A substance that, when dissolved in water, produces a solution that conducts electric current very efficiently is called what? Well, if it conducts electric current, it is an electrolyte. If it conducts efficiently, it's a strong electrolyte. So that's why this one is the correct answer. It's not just an electrolyte, it's a strong electrolyte. $76. What type of reaction is this? It's already balanced for us. Silver oxide yields what? Silver, solid, and this is solid, plus oxygen. Okay, what type of reaction is this? Well, remember when you've got a compound and it yields elements, that's a decomposition. So it's definitely a decomposition, C. It's a decom. Okay, what else is it? It's not a synthesis, that's the opposite of decomposition. It can't be both. Is it a combustion? No, there's no oxygen reactant here. Can't be a combustion. How about oxidation reduction? Remember the trick I gave you. If one of the elements is pure on one side and then a compound on the other, that's an oxidation reduction reaction. And we've got two cases. That's in a compound over here, that's in a compound over here. This is a redox reaction. B. Right? So it's two of the above. A is the correct answer. All right. $77. It's like we're into identifying reaction types here. Water, in what type of reaction is water always a product? Now, this goes back to the reaction of an acid and a base. Always produces a salt. All right, this is an acid. This is a base. Always produces a salt plus water, right? Hydroxyl plus hydrogen, right? HOH, HOH. This type of reaction always produces water. Acid-base reaction. Now, other reactions can produce water, that's true, but an acid-base reaction always makes water. All right, number 80. The factors that most commonly cause chemical reactions to occur are all of the following, except, let's see, a decrease in temperature. Will that cause a reaction to occur? Most likely not. If you need a reaction to occur, you need to add energy to it. That means you increase the temperature. So A is false. That's the exception. Transfer of electrons, that's a redox reaction. Yes, that will cause a reaction to occur. Formation of water, such as acid-base reaction. Yep, that will cause a reaction. Formation of a gas. Yep, that will drive a reaction. Formation of a solid, that will drive a reaction also. So the only one that's wrong there is A. All right. Let me scroll that one just a tad. Yeah, maybe I can do both of them. There we go. 84. An aqueous solution of ammonium sulfide. Ammonium sulfide. Sulfur is in the same group as oxygen, which means it's a 2- charge. This is a 1+ charge, so we need 2 of these. That's the correct formula for ammonium sulfide. And it's in aqueous solution. We allow it to react with an aqueous solution of barium chloride. Barium chloride. This is a 2+ charge because it's an alkaline earth. That means this one has to be a 2 there, and that's aqueous. All right. And what do we form? Well, this is a double replacement. You swap parts. Barium goes with sulfur. Barium, sulfur. They're both, that's a 2-, 2+, that's it. And ammonium chloride. And they're +1, -1. And you look it up in your solubility chart and you find that ammonium chloride is soluble. Right? So it's an aqueous solution, but barium sulfide is a solid. Okay. That was kind of hidden over there. I'm sorry about that. Now it wants us to give you the coefficient for the solid. So we need to balance the equation. Right? You got ammonium here, you got ammonium there. Oops, sorry. There's a 4. Ammonium chloride. So if we put a 2 here, it gives us 2 ammonias. That gives us 2 chlorides. We get 2 chlorides here. We got 1 sulfur, there 1 sulfur, but that's it. It's balanced. So the coefficient in front of the solid is a 1. $85. The equation. This is ethane. It's an organic gas. Hydrocarbon plus oxygen yields 4 carbon dioxide and 6 water as an oxidation reduction reaction. Yeah, true or false, and why? Okay. Is it an oxidation reduction reaction? Yes. All combustion reactions are redox reactions. Look here. There's your clue. That's a combustion reaction. This is an oxidation reduction reaction. It's true. So it's either this one, this one, this one, or this one. Can't be D. So why is it? Well, the carbon is reduced and the oxygen is oxidized. Okay, so now we have to determine what's what. So let's put the equation up here and do some calculating. Excuse me, that's not right. H6, 7O2 yields 4 CO2 plus 6 H2O. All right. In order to explain, notice that we've got the choices. Carbon is reduced or oxidized. Carbon is oxidized. So let's find out what's happening to carbon first. So what's carbon on this side? Well, hydrogens are +1 oxidation state. That means +6 total. And that means we need a -6 here, but we got 2 of them. So this one's a -3. On this side, carbon, oxygen is a 2- oxidation state. So it's -4 total. That means this has to be a +4. So what happened to go from carbon there to carbon here? It went from a -3 to a +4. How do you go from a negative to a positive? You have to lose negatives, lose electrons. So we lost how many electrons?
Well, from 3 to 0 is 3, and from 0 to 4 is 4, so that's 7. Lost 7 electrons per carbon.
Okay? So if carbon loses electrons, remember the mnemonic device, oil rig, oxidation is loss. So carbon is oxidized. So it could be this one or it could be this one. Now, what about hydrogen is reduced or oxygen is reduced? Let's see. Oxygen is a zero oxidation state, and it goes to a -2 here and a -2 here. So oxygen gained 2 electrons per oxygen. Oxygen was reduced. So if carbon is oxidized and oxygen is reduced, the answer has to be E. In fact, nothing happens to hydrogen. Hydrogen +1 here, and it's a +1 here. Nothing happened to hydrogen. It's carbon was oxidized and oxygen was reduced. All right. 86.
What do they want us to do with 86?
How many electrons are transferred in the following oxidation reduction reaction?
Okay, so let's write it out. There's zinc, and it's reacting with silver nitrate in solution. Yeah. And it produces zinc nitrate. Okay. Plus 2 silvers. So what are the oxidation states here? Well, the elements are always zeros. Zero oxidation state. The nitrate is a polyatomic ion with a -1 charge. -1 charge. So that means silver has to be a +1. And zinc has to be a +2 to balance 2 minuses. So now that we have all our oxidation states, we can say how many electrons are transferred. Well, if we go from this zinc to that zinc, we had a loss of 2 electrons per zinc. Now let's see if it's balanced, we should get the same gain here. Gain 1 electron per silver, but there are 2 silvers, right? 2 silvers equals 2 electrons. So how many electrons were transferred? 2 electrons. 2 electrons were transferred in this balanced equation. '89. An aqueous solution of sodium carbonate is allowed to react with an aqueous solution of magnesium chloride. The complete ionic equation contains which of the following species when balanced? Okay, so we've got to write out the compounds first. Sodium carbonate. That is a 2- charge. This is a 1+, so we need 2 of them. And this is aqueous solution. Okay, I'll go with that. And then we have magnesium chloride is the other reactant. Okay, this is aqueous solution. And that produces magnesium combines with carbonate. Right, 2-, 2+, that's balanced. And then sodium chloride, table salt. We know that that is soluble. That's an aqueous compound. Right, it's in aqueous solution. How about this one, magnesium carbonate? Look it up in your solubility chart, and you'll find that it's a solid. Right, that's your precipitate. Okay, we've got these written correctly. Now we need to balance them. Well, let's see. We got 2 sodiums here and 2 chlorides. What if we put a 2 here? That'll give us 2 sodiums, 2 chlorides on that side, 1 magnesium, and 1 carbonate. That's it. Okay, that's the balanced, complete molecular equation, we call it, or a formula equation. So how do we write the complete ionic equation? That's the next step. Well, we got 2 sodiums, and we have, and that's aqueous solution, and we have 1 carbonate in aqueous solution. We have 1 magnesium in aqueous solution, and we have 2 chlorides in aqueous solution. Okay. Then we have our solid, and we have 2 sodiums and 2 chlorides. Okay, that's our complete ionic equation. Now, if we're going to have, that's as far as we need to go, complete ionic equation. Okay, which ones of these are located in there? And notice we've got coefficients here, so we have to take that into account. Sodium. No, we've got 2 sodiums here, 2 sodiums there. That doesn't work. 2 carbonates. Nope, just 1 carbonate on this side. 2 magnesiums. No, just 1. Chloride. We need 2 of them. There's only 1. 2 chlorides. There you go. There's 2 chlorides there. There's 2 chlorides there. So E is the answer. That's the one. All righty. Do some more scrolling. 96. Yeah, we can get the whole thing on there. 96. And we're good for time. An aqueous solution of ammonium sulfate is allowed to react with an aqueous solution of barium nitrate. Identify the solid in the balanced equation. All right. Ammonium sulfate. Ammonium sulfate. This is a 2- charge. This is a 1+. So we need 2 of these. That's aqueous solution. Barium nitrate. Right? Barium nitrates. All nitrates are soluble. But this one is a -1 charge and this is a 2+. So this one has to be 2 of those. Now, what is that going to give us? Well, this is a double replacement. Barium goes with the sulfate and ammonium goes with the nitrate. So the barium sulfate is like that. 2+, 2-. That's good. And then ammonium nitrate. 1- and 1+. That's good. And you find out that's aqueous. Right? Look it up in your solubility chart. Look this one up in the solubility chart. You find it's solid. Okay. But do we need to balance it? Well, we need 2 ammonias. And that gives us 2 nitrates. We got 1 sulfate and 1 barium. That's balanced. So, which one is the solid? It's barium sulfate with a 1 coefficient. Right here. Okay. Right. That was 96 and 97. Okay, let me scroll a little bit. This one might be a little difficult. Yeah, we can't get the whole thing on there. Okay, I'm gonna bring this one down. Just a little bit more. How about 95? Not quite. How about 90? There we go. That's good. It's a little more difficult to see, but now we've got everything on the same slide. 97.
And when you're viewing this video, if you want a better look at it, just get your review document and open it to the 97, and then you'll have it in front of you so you can watch while I'm talking. Which drawing best represents the mixing of an aqueous calcium chloride, aqueous, with an aqueous potassium sulfate? Okay. So when those mix, potassium goes with the chlorine, which is aqueous, and then the calcium goes with the sulfate, which is a solid. Okay. Now we need to balance. So we need two of these here, two potassiums, two chlorines, one sulfate, one calcium. That's balanced. Okay, which one of these best represents that? Well, notice that we've got on the left-hand side of the arrow, these are the reactants. So these are the separate reactants before we put them together. Okay, and what we're looking for is one calcium, two chlorines, two potassiums, and one sulfate. So let's see, which one has one calcium? There's one calcium chloride. That's correct right there. That's A. There's a calcium chloride. That's correct. B is correct at this level. C, no, that's wrong. This one's correct, D. That one's not correct because the chlorines are bound together. So we're starting off, we've got a possibility for D, B, and A. Now we'll go to the next one. We need two potassiums and one sulfate. So that one works. And that one works. And our other one was this one. That's two potassium. Okay, so it could be A, B, or D. Now we look at the product side. Notice we've got a precipitate formed. That's what that black at the bottom means. That's the precipitate. Right? So we have a solid formed. We got A, B, and D as possibilities. A doesn't have a solid, so A is out. So it's either B or D. What's in solution? We've got potassium and chlorine. But notice, let's see. Did I say yes? It's either B or D. We've got two potassiums and two chlorines with the solid on this side. Whereas on this one, we only have one potassium and one chlorine. So, well, that one's out anyway. That's a C. It has to be this one. Right? Two potassiums, two chlorines, one calcium, two potassiums, one sulfate. And that satisfies this arrangement. So the answer has to be B. That's how we decipher that type of problem. Process of elimination. All right. So let me find my next one and then I'll blow it up some. So we can see it better. Let's go back up to, I think I was 160. Yeah. There we go. We get 103 and 104 at the same time. (103) Use the following choices to classify each reaction. Let me check something here. Use the following choices to classify each reaction given below. More than one choice may apply. Okay, so here's the reaction. We got 2 cesiums plus a fluorine gas yields 2 cesium fluoride solid. Okay. Well, what do we got? Well, in the first place, we have 2 elements make a compound. That's a synthesis. Do we have synthesis up there? Yes. C is true. We also have an element in a compound. That's an oxidation reduction reaction. So we have one of those. Yes, we do. A, oxidation reduction. What else do we have? Combustion? No, there's no oxygen. Decomposition? You can't have both a synthesis and a decomposition at the same time. So A and C are the correct answers for this problem. 104. Use the following choices to classify each reaction given below. Okay. So here it is. We have sodium sulfate, aqueous, plus lead 2 nitrate, aqueous, yields lead 2 sulfate, solid, plus 2 sodium nitrate in solution. Okay, what type of reaction is this? Well, notice that these are aqueous, 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 solid. That's a precipitation reaction. All right, so that's C is a possibility. How about acid base? Neither one of those is an acid or a base, so it can't be B. How about A, oxidation reduction? Well, let's look at their oxidation states. Sodium is a +1 here and +1 there, nothing changed. Sulfate here is entire, sulfate there is entire, no change there. Nitrate's entire, nitrate's entire, no change there. This is a lead 2+, this is a lead 2+, right? So no oxidation reduction. The only one that fits is precipitation. All righty. 105. What's our reaction? 4 ammonias. 4 ammonias. Okay. 5 oxygens. 5 oxygens. Yields 4 nitrogen monoxide and 6 waters. And that's a gas. Okay, what do we got here? We've got an oxygen as a reactant. That is a combustion. So do we have that one? Yes, B is true. Combustion. What else do we have? Well, all combustion reactions are oxidation reduction. So is that one up there? Yes, A. Okay. So we have those 2. What about the other? Synthesis? No, we're not making a more complex out of simple. Decomposition? No, we're not making simple out of complex. So the only 2 up there that work are A and B. Okay. 106, let me scroll and maybe I can do both at the same time. Okay, we got 3. Yeah, let's do that. 106. Our reaction is sodium solid plus, that's supposed to be a plus sign right here.
plus nitrogen gas yields what? 2Na3 in solid. Sodium nitride. Okay, what kind of, well, we got elements making a compound. That's a synthesis. But is that one of the, no, synthesis is not up there. So we have an element here, an element here, and a compound there. This is a redox, which is A. How about B? Acid base? Nope. Precipitation? Nope. Even though we got a solid here, it's not formed from two solutions. So it's not a precipitation reaction. So A is the only proper answer here. How about 107? What's Hg? Mercury plus oxygen gas yields 2HgO, mercury 2 oxide, solid. Go. Element, compound. That's a synthesis. Is that there? Nope. But this synthesis is also an oxidation reduction reaction. Right? So we got that one. That's A. It's not an acid base. It's not a precipitation. Okay. So 107 is like 106. Same type of reaction. (108). Let's see. Let me scroll just a hair so I can be sure to get the bottom. There we go. 108. Gallium nitride. 2 gallium nitride solid yields 2 gallium solid pure element plus, that's another plus sign, nitrogen gas. Okay. What we have here is a decomposition. Is that there? Yeah, D. Okay. So that's a decomposition. Notice also element compound. This is a redox reaction. Oxidation reduction. It can't be a synthesis. It's a decomposition. It's not a combustion. There's no oxygen there. So these are the only two, A and D. (109). Let's see. HC2H3O2 in aqueous solution, and then cesium hydroxide in aqueous solution yields what? Water plus cesium. Let me write it down here so I won't get covered up. Cesium acetate, aqueous. Okay, notice that this is the acetate polyatomic ion with a hydrogen in front of it, which means it's an acid. That's acetic acid. This is cesium hydroxide, acid base. This is an acid base reaction. It produces a salt and water. It's not a precipitation. It's not an oxidation reduction. There's been no change of oxidation states. This is intact. This one is an OH minus with an H plus, makes an H2O neutral. All you did there was neutralize charges. You didn't change oxidation states at all. So B is the only possible answer. It's an acid-base reaction. Okay. Scroll it again. And let's see, can we get that one? Yeah. Okay, 110 to 111.
110, which is carbon
solid, excuse me, plus oxygen, gas, yields what? Carbon dioxide. Gas. Okay. This is a synthesis, right? Elements, element, compound. So is that up there? Yes, C. And it's also a combustion. Oxygen, combustion up there. Yep, B. And all combustion reactions are redox reactions. Is that one up there? Yep, A. Leaves D. D is not, it's not a decomposition because it can't be both. It can't be a synthesis and a decomp. So it's A, B, C is the answer to 110. (111). So we have HNO3. What is that? Nitric acid plus sodium hydroxide. Probably see where this one's going. Makes water plus sodium nitrate in solution. Okay, that's an acid-base reaction. B. It's not an oxidation reduction. It's not a precipitation. That's all it can be. It's just B. All right. 112. KBr in solution. Okay. Plus what? Silver nitrate in solution. See where this one's going. Is it going to make a solid? Silver bromide. Yes, it is. Plus potassium nitrate still in solution. This is a precipitation reaction. Two solutions, aqueous compounds, forms a solid. So that would be oxidation. It would be 112 would be C, precipitation. It's not an acid base. There's been no oxidation reduction take place here. That's a +1, +1. That's a -1, -1. This is a +1, +1, and nitrate didn't change. So it's only a precipitation, nothing else. 113. Let's see, calcium solid plus hydrogen gas yields what? Calcium hydride solid. This is a synthesis, element compound. Is that one there? No, it's not. How about element in the compound is oxidation reduction? How about that one? Yeah, it's there. It's not an acid base. It's not a precipitation. So it can only be oxidation reduction. Oops, scroll time. There we go. We get those two together. 114. Let's see. Zirconium solid plus oxygen gas yields zirconium oxide. Okay. What do we got here? Well, we've got a synthesis. Is that up there? No, it's not up there. We've got a combustion. That's not up there. But what else is a combustion? Oxidation reduction. All right. So A, yeah, A is true. Oxidation reduction. It's not a precipitation. It's not acid base. So redox reaction is the only one that works. 115. So we got zinc solid plus hydrochloric acid I bet this is a single replacement. We're going to swap places with hydrogen and nitrogen. Aqueous, and I got them out of order. And then hydrogen gas. Okay, so we got zinc element here. It's in a compound there. That's redox. Is that possible? Yeah, oxidation reduction. That's true. Acid base? Nope. There's an acid, but there's no base. Precipitation? Nope, there's no precipitation there. The only possibility is redox. (116). Let's see, H2SO4, aqueous. Yep. Plus barium hydroxide makes what? I bet it makes water. There's water. Plus barium sulfate. Solid. Ooh. Now what do we do? Well, we've got a solution, an acid, and a base. Makes salt and water. That's an acid-base reaction. Right? So that's B. That's true. What else do we have? We've got two solutions mixed together and make a solid. That's precipitation. Right? Even though it's also acid-base, this is a precipitation reaction. So C is also true. And oxidation reduction, no. There's been no change in oxidation state for any of these elements. 117. All right. Zinc 2 bromide in solution, yes. Plus silver nitrate. Silver nitrate in solution yields what? Zinc nitrate, zinc 2 nitrate in solution plus 2 silver bromide solid. Okay, so we got to precipitate here. This is a precipitation reaction. Two solutions make a solid. Oxidation reduction, no oxidation states changed here, no acid bases. So precipitation is the only one that satisfies conditions. All right, 118. We got a lot of these, don't we? I only got 10 more minutes. 118. I may have to stop writing them on the board. Okay, 118. I'm not going to write this one in the interest of time. So what do we have here? We've got a hydrocarbon with oxygen makes carbon dioxide and water. That is a combustion reaction. So B is a candidate. Remember, all combustion reactions are redox reactions. So it's also A and B. It's not a synthesis. We're not making something complex out of simple, and it's not a decomposition. So A and B are the only two possibilities. About 119. All right, we got elemental phosphorus plus elemental oxygen makes P4O10. That's a synthesis. So C is a valid answer. It's got oxygen, that's a combustion. B is also. And we've got elements on this side in a compound on that side makes redox. So it's all three: oxidation reduction, combustion, and synthesis. (120). Okay. We have a similar situation here to the one before. We've got a synthesis, simple to complex. We've got elements in a compound, redox, and we have combustion. So this one is also ABC. How about 121?
So we have mercury 2 oxide yields mercury and oxygen. Okay, this is a decomposition, not a synthesis, decomposition. It's not a combustion because oxygen's not a reactant. And we've got a compound on this side and elements on that side. It is an oxidation reduction. So we got redox and decomposition are correct answers for the 121. (122), let's scroll a little bit. Okay. (122). So we have hydrochloric acid and lead 2 hydroxide yields lead chloride plus water. So we got an acid and a base, produces a salt and water. That's an acid-base reaction, there B. We also, in this process, produced a solid. So this is a precipitation. You got acid-base and precipitation, and there was no change in oxidation states. So 122 is B and C. 123. All right. Sodium and hydrogen make sodium hydride. That's a synthesis. Is that there? Yeah, there's a synthesis. It's also a redox reaction because we're going from element to compound. Oxidation reduction. It's not a combustion, can't be a decomposition. So A and C are the correct answers for this one. (124). Water yields hydrogen and oxygen. This is a simple reaction to conduct in the laboratory. All you need is a 9-volt battery, distilled water, and a little bit of acid. Hydrochloric acid works great, just a drop. And when you drop that battery in the water, the electron transfer will split this. It will decompose water into hydrogen and oxygen. And in the process, also demonstrate a redox reaction. So this is decomposition and redox. It's not combustion. It's not synthesis. So A and D are the only 2 answers for that one. Let's see here. Got any more? Should be. There's one. Balance the complete ionic equation when aqueous barium hydroxide reacts with an aqueous hydrochloric acid. This one should be fairly simple. I've got 5 minutes. Let me see how many more I've got to do. 136. Okay, I'm not going to stop on this one because it's really simple. This is an acid-base reaction. There's your base, there's your acid, and water is formed as a pure liquid. Okay. So I'm going to let you do this one or look it up in the worked problems. I'm going to move on to one that requires a little more work so I can get it in before we have to quit. And it's this last one here, 138. Okay. There's more to it. I'll scroll down as we need. So we're given this word problem and we have to be able to write the compounds correctly. That's where we start. So we're reacting. Let's see. We want the molecular, the complete ionic, and the net ionic equation for this following reaction. aqueous copper 2 nitrate.
This is a -1, that's a +2, so we need 2 of these, and it's in solution.
We react that with sodium hydroxide.
That's an aqueous solution also. So what does it produce?
Does it tell us? Yeah, it tells us. Copper 2 hydroxide.
Solid plus
Sodium nitrate.
there.
Okay, so let's balance it. This one should balance fairly easily.
We've got 2 nitrates here and only 1 there, so let's put a 2 there. So that makes 2 nitrates, 2 nitrates, 2 sodiums. We need 2 sodiums here. 2 hydroxides, 1 copper, 1 copper.
That's balanced. Okay. So next we need the complete ionic equation. The complete ionic equation is if it's in aqueous solution, then the reality is you have individual ions floating around in that solution.
We have a copper 2. See, I'm going to stretch over here. Copper 2 plus in aqueous solution. We have 2 nitrates in aqueous solution. We have 2 sodiums in aqueous solution. And we have 2 hydroxides in aqueous solution. Now on this side, we have the solid. 2 copper hydroxide. Oops, my mistake. That should be a 2 and solid. And then we have 2 sodiums in aqueous solution plus 2 nitrates in aqueous solution.
That's the complete ionic equation, and it should match that one. Now we need the net ionic equation. So how do we do that? Well, you look on both sides and find common elements.
Okay. Copper 2 plus, no. Nitrates, 2 nitrates. Yep, that goes out. And 2 sodiums, 2 sodiums. 2 hydroxides, they're in here. So the net ionic equation is that plus that yields the solid.
And this is actually the driving force for the reaction. When you get this one together with that one to make a solid, that drives the reaction toward completion. Okay, that's it.
And right on the button.
Okay, we're done for today. And this is Tuesday. So Thursday is the exam on this material. Just check myself here. Yes. On the 9th, March 9th will be the midnight or 11:59. March 9th will be the deadline for this exam. And I'll be in the classroom in case you want to take it in person. And I'll also be zoomed in case you have questions. So that's it for today.